Okay, so assume that the seed triangle of the Coke snowflake has area 324. So I believe this is number 3. So we've got a table here where we have start, and then we have R is number of triangles added. And then S is the area of each triangle added. And T is the total new area. And Q is the area of the snowflake. So for me, it helps to replace all those letters with what the things actually are. And we did this last class, but we had a different seed. Okay? The area of our seed was something else, I forget. I think, no, it wasn't 1. I forget what it was. All right, so they tell us at the start, we're not adding any triangles on, 0, 0, and the area of the entire snowflake is just the area of the seed, 324. Okay, so then at step 1, so maybe I should draw a picture to help keep track of what's happening here. Here's my seed triangle. It has area 324. Step 1, I'm going to add some equilateral triangles on. So I added 3 triangles, so I can put that in my table. Number of triangles added 3. The area of each triangle. So last class, we found the area of each triangle using a formula, right? You have to know the length of the side to get the area of the triangle. But picture something for me. These 3 triangles are all the exact same size, right? Imagine folding them in on top of the original triangle. And then if I put in these lines here, if I folded them all in, though they are this one, and this one, 3 out of how many completely equal triangles that fit on top of the original surface? There are 9 triangles, all exactly the same size. 3 of them are the ones that I attached. So each of these is 1/9 the total area of the triangle. Does that make sense? Each of the triangles that I'm attaching is 1/9 my total area. So 324 divided by 9. $36. Oops. So the area of each triangle is 36, and I'm adding 3 of them. 3 times 36 is 108. So that's my new area that's being added on is 108. Add that to the area we had before. 324 plus 108 is 424, 432. Okay. Then at step 2, I add more triangles. Okay, so at step 2, I go to this picture and I'm going to put a little triangle on each piece here. So there are 12 pink triangles that I'm adding. 12 triangles. I need to figure out the area of each one. So each one of these pink triangles is going to be 1/9 the area of the little triangle it's attached to, just like each triangle was 1/9 the triangle it was attached to in the previous step. So I know that each of these triangles has area 36. So each of these triangles is going to have area 1/9 times 36, which is 4. Because I could fit 9 of these little triangles in the step 2 triangles. Oops. So each area of each triangle I'm adding is 4. 12 times 4 is 48. 432 plus 48 is 480. So you just continue this way to finish filling out the table. Yes. Times 4. The next one will be times 4. And then these will always be times 1/9 times 1/9. And then you multiply these two to get this one. And then for the very last, for part B, they're asking what is the area at infinity? The area of the final Coke snowflake, we know, is always 1.6 times the area of the seed, which was 324. $518.4. You're welcome. Yes. Uh-huh. The way we build this triangle is to start, this gasket is to start with any triangle. It does not have to be equilateral like the Coke snowflake does, but that's often how people draw it because we like equilateral things. So you start with any triangle and remove its middle. So what removing the middle means is if you have a triangle, to remove the middle, put the midpoint of each side down. So draw the midpoint of each side, connect them, and this is considered the middle. And we remove it, throw it away. Okay, so you're only left with these triangles. And then you do the same thing over and over again to every triangle that still exists, remove its middle. So here's a picture of several steps. So here's my seed, any old shaded triangle, connect to the midpoints of every side, and remove the middle. Okay, so this would be step 1. Empty, this is empty space here in the middle. Now with every orange triangle that exists now, to get to step 2, connect the midpoints of every side and remove. So you just take those out and now we have more empty space in the next step. And then do it again to get to step 3. Now we have 9 triangles. For each of them, connect the midpoints of all 3 sides, remove the middle, and you get step 3. So does the construction of it make sense? Not too complicated, pretty clear rule. After a few more steps, our eyes can no longer tell the difference between one step and the next. So this is the Sierpinski gasket at step 7. Step 8 wouldn't appear any difference to us because eventually the triangles that we're removing are so tiny you can't even tell that they were removed. So this is an approximation of the Sierpinski gasket. Like the Coke snowflake, you can't ever finish drawing the Sierpinski gasket. It's an infinite object. The actual gasket is the shape that we would obtain after an infinite number of iterations. So it can only exist theoretically in our brains. You can't ever create this thing. We can only create approximations. But despite the fact that it can't ever exist in the real world, there are things that we can know about it for sure. Okay? Even though we can't draw it, we can know some things about it even though we can't actually measure them. So the first is that, again, like the Koch snowflake, you have infinite, universal, and exact self-similarity. You can zoom in on any part of the gasket, blow it up, and it looks exactly like the original. So I'm just going to tell you that the perimeter tends towards infinity. Do you believe that believe it? That the perimeter just gets longer and longer? The length of its edge. So let's look at the first few steps here. In step 1, my perimeter would be, let's just say each side has length 1. My perimeter would be 3, right? And then in step 2, I have that original 3 plus 1.5. Right? If we're talking perimeter as being the edge and not just the outer edge. Okay. So this one, we still have the perimeter of 3 plus the 1.5 plus, I don't know, those would be a quarter, so 3/4, 1.5. 2.25. So does it make sense that this perimeter just gets longer and longer? Yeah. If we think about perimeter as being every edge and not just the outer edge. So perimeter goes to infinity, as just like the Koch snowflake. Perimeter goes to infinity. But we're not going to investigate this one in any depth. We're not going to get a formula for the perimeter at each step. It's good enough to know that it just gets longer and longer. All right, so let's investigate the area. So look at step 1 to step 2. Step 1, we have, let's just say that the area of this original triangle is 1. What percentage or what fraction of the area still remains after we've thrown out the middle? 3/4, yeah. So I broke this original triangle into 1, 2, 3, 4 equal triangles, throw out one of them and keep 3 of them. So I still have 3/4 of the area. I threw away 1/4. All right, what about when I go from step 1 to step 2? 3/4 again, because I just I threw away 1/4 of every existing triangle. I kept 1/4. So I could demonstrate it by saying, okay, well, right now in step 1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 triangles, right, total. I'm going to throw away 3 of them, which leaves me with 9/12 of what I started. I get to keep 9 of them. And 9/12 is 3/4. Step 2 to step 3. How much do you think I'm going to still have? How much area? Same thing, 3/4. 3/4 of the area remains. Every step, you're throwing away 25% of what you have. You're throwing away the middle, which is 1/4 of every existing triangle. So you're keeping 3/4 of every existing triangle. So given the fact that we are keeping 3/4 of the area, I want to write a recursive and an explicit formula for the area at step n. So let's see, recursive, explicit. So we'll say the area at step n would be what? In terms of the area at the previous step. Yes. Not times n, times a sub n minus 1. Yeah. 1 minus a quarter of what you used to have. Right? That is 3/4 of what you used to have. 1 minus a quarter. Actually, there should be parentheses here. Yeah. 1 minus a quarter of what you used to have. So you get to keep 3/4 of what you used to have. So you do 3/4 times a sub n minus 1. And for explicit, they told me for explicit, I can assume the area of the seed triangle was 1. So how would I write a formula for the area, an area that I start with 1, and I just keep taking 3/4 of it? Yeah, so I could start with 1 and subtract a quarter. So I could say, well, or I could just say I'm keeping 3/4. I think that's going to make the formula. You don't add 3/4, but you multiply by 3/4. Yeah. So I'm going to start with 1, and I'm going to multiply by 3/4 every time. And repeated multiplication, we always denote with an exponent. So I start with 1, and I multiply by 3/4 at every step. Get to keep 3/4. So think of this as money in your bank account. I'm going to get back to my original pictures here. This represents the money in your bank account. This is your total balance, right? Let's say at each step, like each month or each year, whatever, we throw away 25% of it. Bank fees. What's happening to the amount of money in your bank account? It's getting smaller. Yeah. And it's approaching 0. Yeah. If you just keep throwing away 25% of your money, you're going to have no money real fast. Or at least no significant amount of money. It's going to be real close to 0. So as we let n go to infinity, a sub n, the area of the gasket, goes to 0. So this theoretical object that can only exist in our brains, the actual Sierpinski gasket, after infinite iterations, is 0. There's nothing left. If you could do this to infinity. It won't go negative, no, because throwing away 25% of something. True, because you can't do something an infinite number of times in real life. In our theoretical infinite world. Yep. Exactly. Yeah. That's why we often use this notation to say it approaches 0. That's what the arrow means. When I write these two notations mean the same thing. When I write a sub infinity, this is like a theoretical magical land where I could do something an infinite number of times. But you can't actually ever do that, and it's hard to conceive of such a place. So often we use this notation instead to say, well, it approaches 0. So nature kind of likes this pattern. Found a shell with what looks like a Sierpinski gasket pattern on it. And it shows up in some crazy places. I'm going to show you 2 of them. Get ready to be blown away. Awesome. So the first one is called the chaos game. We start with an arbitrary triangle. We name the vertices A, B, and C. The 3 corners are going to be A, B, and C, and we're going to roll a dice. A roll of 1 or 2 is going to correspond to vertex A, 3 or 4 to vertex B, and 5 or 6 to vertex C. And here's how the game works. You choose any point in or on or near your triangle. So here's my triangle. I'm going to choose any point. label it P1. Okay. Then roll the dice, and whatever number comes up, it corresponds to a vertex. So let's say we roll a 2, that corresponds to vertex A. I'm going to draw a line from P1 to A. It can be an imaginary line, but you put a line from P1 to A and mark a point halfway along the line, and we call that P2. Then you roll the dice again, and you repeat the process. So you roll, let's say we roll the dice again, and this time we get a 5. That would correspond to vertex C. So from your current position at P2, draw a line to vertex C and put a point halfway between, call it P3. Roll the dice again. Let's say we roll a 4, a 2. Okay, so we're going to go to A. If it's a 2, we would go to A, put a point halfway between, call it P4. So usually you can just do imaginary lines because these lines are going to get really messy, or erase them each time. But leave the points. Leave the points. This is what you get if you play this game for a long time. These are the points. Yeah, so out of chaos, I mean, this is pure chance. Rolling a dice, right? And out of the chaos comes this like unbelievable structure.
So you can win in Atlantic City. Play
Maybe. So we can do this, but I have a little applet that will play really fast because it takes a long time for the structure to emerge. So here's my triangle. I'm going to show the iteration so that you can see the rule, how they're following the rule. And I'm going to make the pixels a little bit bigger, maybe 5. And to start, we're going to go kind of slow. We'll go 200. So it picks a random point to start, and then it's just rolling a dice and following the rule. Going halfway to the vertex, putting a new point. So it is, do you agree that it's fairly playing the game? It's doing it the way it's supposed to? Okay. So I'm just going to speed it up. Make it like 10. Yeah. So now we're just playing the game really, really fast. I knew it would. And the more we play, the more structure develops. So we get deeper and deeper iterations of the Sierpinski gasket. Like eventually, you know, we can see these little itty bitty triangles within emerging. It's crazy.
Aliens.
Okay, so that's one crazy place that it shows up. Surprising place. The next place that it's going to surprise us is we're going to have to take a couple of slight detours. They're going to seem unrelated, but we'll bring it back around. So first, this is what's called Pascal's triangle. Anybody seen this before? Heard of it? It's a famous triangle that was invented or discovered, I guess, by Blaise Pascal, who's a French mathematician in like the 1600s. Yeah, it has a very similar pattern to Fibonacci. So the structure of this triangle, the way you build it, is really pretty simple. But we're going to see incredible structure emerge from this simple rule. Okay. So you start with 1, 1, and 1 up at the top. And then along the sides, you always have 1s. And every other entry, besides the 1s along the side, is the sum of the 2 numbers above it. So this 1 and this 1 makes a 2. Right? 1 and 2 makes the 3. 3 and 3 make 6, 1 and 3 make 4. Everybody see it? So the two numbers above it make the number below. That's kind of like the Fibonacci rule, right? The two previous numbers make the next number. So the next line in Pascal's triangle, we always have ones on the outer. So we've got ones there. And then each entry will be the sum of the two numbers above it. So 1 and 7 is 8, 7 and 21 is 28, 56, 70, 56, 28, 8. So we could just continue this triangle forever, right? Just taking the two numbers, adding them together to get the next entry. So part of the reason why this triangle is so famous, despite the fact that it's very simple to make, is that there's tons and tons of hidden structure. That once you start to look more closely at this thing, you start to see all kinds of patterns. So I'm just going to show you, I don't know, 2 or 3 or 4 of the more immediate patterns in here. But mathematicians have been studying this for 400 years because there's so many interesting patterns to be found. So I'll show you a few of the more obvious ones. One is called the hockey stick pattern or the sock pattern. So if you look at any hockey stick, add the numbers in the tall part of the sock and it equals the number in the toe. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. And you can do it anywhere, as long as you start on an edge, you can do that anywhere in the triangle. So you can do small ones, like 1 plus 6 plus 21 is 28. You can do big ones, just kind of an interesting pattern. Let's see, what happens if you add the numbers going across? So like 1 plus 1 is, well, sorry, just 1 is 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 10, 14, 16, 32. These keep doubling. We end up with a geometric sequence or exponential growth. Constant ratio of 2. So these are the powers of 2. What if I look at the rows as numbers themselves? So I've got 1, 11, 121, 1,331, 14,641. Is there anything special about those numbers? They're squares of each other? 11 squared is 121. Yeah, 11 squared is 121. That's part of the pattern. Good thing to recognize. What? Yeah, they're all times 11. These are powers of 11. Now we have a geometric sequence, another geometric sequence where the constant ratio is 11. 1 times 11 is 11. 11 times 11 is 121. 121 times 11 is 1331. 13 times 11 is 14,641. Pattern continues. All right, I'm going to show you the best one. I'm going to draw some diagonals through the triangle, and we're going to add up every number that my line goes through. That diagonal just goes through a 1, right? And I'm going to go down 1 more. That diagonal just goes through a 1. What's the sum of the two numbers we go through? 2. Three. Goes through 1 and it goes through 2. 5. 1 plus 4 is 5, plus 3 is 8. Those are Fibonacci numbers. Crazy. So we have tons of patterns. I showed you a couple of the more obvious ones, although the Fibonacci numbers are pretty hidden, but they're in there. So I'm not really going to hold you responsible for these patterns like on a test. I just wanted to show you the many cool, interesting patterns in Pascal's triangle. All right, second detour. So first one is Pascal's triangle. The next one is the arithmetic of remainders. So remember when you first learned long division and you would, at the end, you would just write remainder 2, like instead of doing anything with that remainder? We're going to do that again today. So if I divide 20 by 6, if I do long division, you would go, oh, well, 6 goes into 20 3 times. 3 times 6 is 18. And my remainder is 2. So what is the remainder when I divide 20 by 6? 2. Only care about the remainder. I don't care how many times it goes in. I just want to know the remainder. So what's the remainder when you divide 28 by 7? 0, because 7 goes in an even number of times. 0. Now, here's a trickier one. What if I divide 2 by 4? 2 divided by 4. So if I were to carry out the long division, I would ask myself, how many times does 4 go into 2? Right, but I'm not dealing with decimal points because that's what the remainder does. The remainder is the decimal part. But you said it doesn't, right? 4 goes into 2 0 times. 0 times 4 is 0. Remainder is 2. So when I'm dividing a number by a number that's bigger than it, the remainder is the dividend itself. And if you ever forget that, just carry out the long division. So that one's a little bit important and it's tricky. All right, so we can always find remainders by just doing the long division. Let's say I want to divide a number by 2. Any number. What are the possible remainders I could get? 0. 2 could go in evenly. Yep. Any others? 1. I could have 1 left over. What? That's it? Why not 2? Why can't 2 be a remainder? Yes, because if 2 were my remainder, then I could actually put 2 in a whole nother time and my remainder is 0. Does that make sense? So these are the only 2 possible remainders, 0 and 1. Right. So you can take any number and reduce it to 0 or 1 by dividing by 2, okay, and just giving the remainder. So a number that when you divide it by 2 and you get a remainder of 0, we have a special name for that. What is that? Even. And numbers that when you divide by 2 you get a remainder of 1, what are those called? Odd. Okay. So you learn what an even and odd number is when you're very young, but I'm forcing you to think about it in terms of remainders now. Partially because we're going to use it for Sierpinski's triangle, but also because we're going to use remainders in the codes that we learn in the next unit. Okay, so don't forget this. All right, what if I wanted to divide a number by 3? What are my possible remainders? Yep. What else? 1 and 2. Why can't I have 3? Because then you could put 3 into 3 and the remainder is actually 0. Yeah. So you can't get a remainder of 3. That just means you did it wrong. You did your long division wrong. All right, so what I want you to do, you have a large Pascal's triangle on the next page. Take each number in Pascal's triangle and divide it by 2. If the remainder is 0, color it one color. And if the remainder is 1, color it another color. So that is, if it's even, color it one color. And if it's odd, color it another color. If you don't have 2 colors, just shade one of them and leave the other one white. Okay. Here's my My coloring. I put a smiley face on all the evens. What do you see? What structure is emerging? The Sierpinski gasket. Yeah, we're getting the triangles in Sierpinski's gasket. And this last row at the bottom is going to make another giant triangle if we continued Pascal's triangle down. So the reason this structure emerges has to do with the fact that when you add two even numbers, what do you get? An even. An even plus an even is always an even, right? So whenever I have two smiley faces, I always am going to have a smiley face underneath. Right? Okay. And so even plus even is even. Let's think about it in terms of remainders. If we have remainder 0 plus another remainder 0, the remainder will still be 0. Now, what if I add an odd plus an odd? What do I get? We get an even. That makes sense because we have remainder 1 plus remainder 1, which actually gives me remainder 2, but that means that 2 can go in again, and I have remainder 0. Okay, so remainder 1 plus remainder 1 is actually remainder 0. The two remainders come together, and now you have another multiple of 2. So anytime you have an odd, you get a smiley face. And the only way you can get a non-smiley face, the only way to get an odd, is if you add an even plus an odd. Remainder 0 plus remainder 1, still remainder 1. So the structure has to do with the remainders. You can also do this as a fun little activity using a divisor of 3. Divide every number in the triangle by 3. Use 3 different colors, one for remainder 0, one for remainder 1, and one for remainder 2. And you'll get another thing that looks like Sierpinski's gasket. All right, so the last thing is that Sierpinski's gasket also shows up, or we can simulate mountain ranges using Sierpinski's gasket. One way, if you wanted to make a realistic looking mountain range, you could do it like this. So start with Sierpinski's triangle, remove the middle, but then before we move on to the next step, I'm going to take each of these midpoints and like jolt them a little bit. Move them some small random amount. And the effect is though the triangle has been jolted like in an earthquake, which is actually how mountains are made, right? So you get this like little twisted gasket, slight jolt. Then you repeat the process. Remove the middles, jolt again. Remove the middles, jolt again. Do it many times, and you get this thing that looks remarkably like a mountain range. Kind of interesting. And just to point out, because the jolt is random, we have self-similarity. This is a fractal because it's a recursive process. We do the same thing. Remove the middles, jolt. Remove the middles, jolt. Right? So it is a fractal, but the self-similarity is not exact. Right? So if I were to zoom in on this little piece here, it would be similar to the original. It would look the same, but it wouldn't be perfectly exactly the same because the jolts have randomness to them. Okay, so my self-similarity would be only approximate. So that finishes up the lecture on Sierpinski's gasket. Anybody have questions?